I'm Rakshita from CSC AML Section C. My topic is parallel implementation of Dijkstra's S algorithm on GPU architecture. Let's get into the topic. Transforming sequential to parallel algorithms. Understand algorithmic principles, grasping the core logic of shortest path calculations, transform to parallel components, breaking down algorithms into parallelized tasks, analyze GPU architecture, identifying GPU features suitable for parallel processing, distribute workload. Oh, GPU features suitable for parallel processing, distribute workload. Allocating tasks across multiple GPU processing units. Dijkstra's algorithm and parallelization challenges. Maintain priority queue organizes mates by distance. Updates neighbor distances. Adjust distances of adjacent modes. Priority queue operations resist parallel decomposition. Operations not easily parallelized. Irregular graph structures cause load imbalance. Uneven load distribution in parallel processing. Extract minimum distance node. Select node with shortest path. Repeat until complementation. Continuous until all nodes proceeds. Data dependencies. Require sequentially ordering. Sequence order jetted due to dependencies. Give a quick overview of the GPU friendly approaches to Dijkstra. SSP present a simple working CUDA implementation that is easy to understand and useful for small to medium graphs. Uses a parallel min reduction plus parallel neighbor relaxation and explain faster, more production ready GPU approaches, delta stepping or bucket approaches, worklist libraries plus optimization tips and pitfalls. High level approaches. When to use what? Classic Digista on CPU uses a priority queue, inherently sequential, extract minimum then relax. Hard to parallelize efficiently. Simple GPU Digista parallel min plus parallel relax. Parallelize the select min step with a reduction of one global minimum per interaction. Then relax neighbor in parallel. Implementation is straightforward but still work in worst case. Same asymptotic as native dense dista. So it's best for smaller medium graphs or when you want a simple GPU port. Which graph representation strategy should be used? Adjacency matrix or compressed sparrow? Adjacency matrix is best for dense graphs, enables coalesced memory access but requires on n square space. Compressed sparse row is best for sparse graphs, memory efficient with op of v plus c space preferred for real world graphs. Worklist or Frontier based SSP, Bleman-Ford or async relaxations. Use iterations where you relax all edges from and achieve frontier like BFS. These maps will to GPUs and avoids global min, but requires more iterations and is essential, essentially Bellman Ford style. Good for graphs with many short paths or where you can accept more iterations. Delta stepping and bucketed triple SP. Very GPU friendly. Edges are relaxed by buckets of distance ranges. It avoids expensive global priority operations and is widely used for high performance GPU triple SP requires turning delta. Library alternates. If production performance matters, use Gunrock, CURock, CUgraph, Rapids, or NVGraph. They implement optimized triple SP or delta stepping and are highly turned. Workfront based parallelization process. Initialize. Set initialize distances and create workfront. Parallelize process. It threads examine neighbors concurrently. Update distances. Use automatic min for safe concurrent writes. Refresh workfront. Select nodes with smaller distances. Which parallelization approach should be used for graph processing? Graph partially realizes corruption but requires boundary centuries. Speculative parallelization, delta stepping hybrid. Enhancing GPU performance. Atomic operation management. Minimizing atomic operations to avoid serialization. Dynamic load balancing. Distributing workloads to prevent bottlenecks. Coalesced memory access. Aligned memory access for efficiency. Shared memory coaching. Storing data locally to reduce global access. GPU graph frameworks. N- NVIDIA CU graph, optimized graph analytics library with GPU acceleration integrated with Rapids for pipelines. Gunrock, high performance GPU graph processing framework supports custom frontier operations and load balanced kernels. OpenCL implementations, cross platforms solutions for AMD and Intel GPUs. Requires vendor specific tuning. Understanding performance. Characterize characteristics based on graph structure. Power law graphs, dense graphs. Power law graphs or load imbalance hinders a parallel performance. Dense graphs or high parallelisms due to uniform workload. Balancing graph algorithm challenges and solutions. Approximately bucket based structures. Approximate bucket based structures provide scalability with low complexity. Billman Ford algorithm has low complexity but limited scalability. Hybrid GPU or GPU approaches often high scalability with complexity. GPU parallelization of Dijkstra algorithm is complex with low scalability. Understanding performance characters based on graph structures. Regular and irregular. Regular to irregular and irregular to regular. Graph density. Higher parallelism achieved. Degree distribution. Load imbalance occurs. Work front size. Increases parallelism, adds speculation. Concrete CUDA example parallel Dijkstra using CSR plus parallel min. CSR graph represents row and PTR column IDX weights. Each iteration compute index of unvisited vertex with minimum dist using a reduction then relax neighbors in parallel. This is simple to understand and runs on GPUs. It is not the fastest possible SSSP on GPU but is a good starting point. Thank you.